Good afternoon. Thank you for the opportunity to discuss an ongoing collaborative research project involving the University of Maine, the University of Rhode Island, which is my home institution, and Hubble Power Systems. The project focuses on the research and development of a novel Vane device to improve helical pile performance for lightweight transportation structures. Before I begin, I'd like to make a few acknowledgements. First, I would like to acknowledge funding provided by the USDOT through the TIDSI program. I would also like to thank my colleagues at the University of Maine, including Aaron Gallant, who is the lead PI on this project, Keith Barabee, who's a co-PI, and Juan Sebastian Carvajal Munoz, who's a master's student visiting from Colombia. I would also like to thank our industry partners, Chance Hubble. They made significant in-kind support. We couldn't have done this project without them. Specifically, I would like to thank Gary Sider, Sean Downey, and the many staff involved. Also thanks to Dennis Asdell from Asdell Hydraulics. Just to give a brief outline of the talk, I'll give you some background on the motivation for this research as well as the objectives. I'll discuss some of our initial field testing we did earlier in the summer, where we think we'll go from here on the research project, and then I'll summarize a few key points. Just some background. I think we've all seen structures like this. These are what I would consider lightweight transportation structures. We have highway signs, lights, and traffic signals. All of these structures have to be engineered. In fact, AASHTO has a specification for the design of these structures, and that includes also the design of the foundation system. I think this slide illustrates well the loads that you might consider in the design of one of these types of structures. This is a cantilevered sign and showing the different loads involved, including the dead load, ice loads, as well as the wind loads on various parts of the sign structure, which can be significant contribution to the load on the foundation. Even though the structure is geometrically fairly simple, it actually results in a fairly complicated loading on the foundation system, which is shown by these red arrows here. So they produce axial, lateral, torsional, and overturning moments at the foundation. For this reason, it's been historical or conventional approach has been to use drill shaft foundations. That those foundations are constructed by drilling the soil out with an auger and then replacing with concrete and steel reinforcement. Now, one of the downsides of that type of foundation is it requires pretty significant equipment and labor as well as time. So one of the things we're looking into is the use of another type of technology, usually referred to as helical piles or screw piles. An example of one is shown in the left photograph here. This is a helical pile is basically consists of a shaft with a helix, one or more helices placed at the bottom, and then the pile is literally screwed into the soil. You can see, some of the advantages are that you need smaller equipment. It can be rapidly installed, and then you don't have to deal with any kind of excavated soils or spoils during the construction process. This particular foundation is a product that Hubble produces for their light fixtures here. Now typically in a helical pile, you get very good axial resistance because you're putting essentially a plate deep down in the soil. However, the lateral resistance really depends on the bending capacity of the pile as well as the passive soil resistance. So sometimes it's the lateral that's somewhat limiting the capacity of these foundations. So the idea is there something we can do to enhance or improve these foundations so that they can be used for larger lightweight transportation structures? So Hubble, actually Sean Downey came up with a conceptual design that they're actually calling the collar vein. It's funny, we had a discussion early in the summer when we were in Missouri about creative names for this thing. So right now, that's the name, and basically what it consists of is a four-bladed vane. For those geotechnicals in the audience, you can see where we get the name. There's something called the vane shear test. It looks very similar. There's a four-bladed vane, and then it's rotated, and it's used to measure the strength of the soil. In this case, we're actually using it to improve the resistance. So the concept that Sean came up with is this two-piece assembly. So one piece has three vanes, and then the fourth vane gets bolted or sandwiched against a segment of pipe pile here, forming the shaft of the pile. So this is the two pieces, and this is showing them assembled. And the idea is you would have a lead section of helicals here, and you would install the pile as usual, and then at some point you would stop, you would assemble this two-piece vane, and then you continue to drive the pile, which will actually pull the vane into the soil. And so from a geotechnical point of view, what this vane is doing is it's essentially effectively increasing the diameter of the shaft. So you get more higher passive resistance to the lateral loading. You also get an increase in the torsional resistance because of the cylinder of soil that's sort of being trapped in between the vanes as you rotate it. So Sean and Gary and their team actually constructed some prototypes, 3 different sizes. This was the largest size. I believe it's a 3-foot height. And you can see here on the photo on the left, this is one piece with the 3 vanes being placed into the pile that's already been driven, partially driven. And then he's assembling the single vane, and then that gets bolted together. And then the photograph all the way to the right showing the driver actually in the process of installing the vane. So as I said, you rotate as if you're installing the helical pile, and that's actually just going to pull or react against the vane and push this into the soil. The objective of the research program really was to investigate the behavior of the collar vane under both lateral and torsional loading. And so earlier in the summer, the team got together in Centralia, Missouri at the Hubble test site to do initial field testing. The site conditions in the Centralia area mainly consist of stiff clay in the upper 25 feet. The undrained shear strengths range from about 0.5 to 2 TSF, and the groundwater does fluctuate within the upper 20 feet or so. So as far as the design and fabrication of the load test system, the pure lateral load setup is shown on the left. So we have the test pile that's being installed. We'll also install a reaction pile with the larger diameter, that's a foot diameter, to give us higher lateral capacity. And then we place a hydraulic cylinder in between those with some structural steel. And then as we actuate the cylinder, it will put the tensile load on the test pile and actually pull the test pile toward the reaction pile, thereby putting a lateral load on. And then what this is showing on the other half here is the dashed line is showing that we can take that setup, and if we install a second reaction pile, we can actually pull in the other direction. So we're able to pull in both directions on a single test pile. For the pure torsional tests, that involved the fabrication of this torsion arm here. And then we take the same setup and we just put it here at the end of the torsion arm. The hydraulic cylinders will actually see the same load because they're wired, hydraulically wired to the same pressure. And then as we actuate those cylinders, they'll apply this torsional load on the test pile. This third cylinder is really just showing conceptually that one of the things we want to look at is the interaction of the torsion and the pure lateral load. So if we can do that, we can get a combined effect if we just reconfigure this to be able to apply both a lateral load and a torsional load. One of the things we had to do is, one of the interests we have in this testing program is to apply cyclic loading. And so we already had, so what we had to do is we had to develop the hydraulic system to do that. We had some of the parts here. So Hubble already had the hydraulic pump. We purchased a couple of hydraulic cylinders that are going to be able to integrate into our load frame. And then this piece of equipment here is a hydraulic controller. It's actually interfaced with a laptop computer, and you can pre-program any time history of loading into the program. And basically what it does, it just controls the hydraulic pressure going to the jacks. And we've used those in the past in doing fatigue testing of piles, and we've been able to put on, for example, upwards of 10,000 loading cycles on a pile. One of the other aspects we were interested in is to be able to measure the bending moment distribution in the pile as during the load testing. So really, Keith Barabee from UMaine was responsible really for instrumenting the pile section, as well as in including all the data acquisition. And I think Keith has nerves of steel here, because I don't know how he's able to wire these tiny little wires on these strain gauges, but he found a way to mount various strain gauges down the pile and wire those. And one of the concerns he has was damage to the strain gauges, was be able to protect them both during installation as well as putting on the vane, because the vane will sort of go around this section and could sort of rub up against the strain gauge and cause damage. So his solution was to develop these thin aluminum collars that he put over the strain gauges, and as I'll show later, they were very effective in protecting the strain gauges. This is actually a nice little team photo. So this is Sean Downey from Hubble. This is Keith. This is Aaron Gallant here, and Juan Sebastian. So for those who may not have seen helical piles being installed, I just have some short video clips here. So this is actually the lead section of the test pile being installed, and it was installed using Hubble's installation driver truck. And the one on the right here is the reaction pile. You can see that that's a much larger diameter to give us some good lateral resistance. This photo is showing now the load test setup for the lateral load. And you can see here that this is the test pile. You have the wires coming out. Those are attached to the strain gauges here and going to the data acquisition system. You can see the hydraulic cylinder here, a load cell, and Sean and his team were able to fabricate some of these connections here, including a turnbuckle, to give us some flexibility in making these and be able to set this up from test to test. What the other thing we have here is not shown is we're using string potentiometers that we attach to the pile. In fact, I think you might be able to see it here. There's a string, and that measures displacement at the pile head location. Just to show some preliminary data here. So we were really just applying some load increments just to see if we can successfully perform the test. Obviously, this is not research quality at this point. This is showing the load over time here, and then this figure below is showing the displacement over time. Typically, if you were doing a load test, you would be trying to maintain the load, each load increment. You can see the load increments are dropping off. We weren't concerned about doing that at this point. We're really just trying to get the setup squared away. But we took the load and the displacement and combined them to generate this lateral load deflection curve here, which is sort of common practice for load testing of piles. These data here on the left are the strain gauge data. So this is strain with time, and you can see the strains for each load increment. And if you take that information and combine it with the sectional properties of the pile, You can calculate the bending moment in the pile, and this is a distribution of bending moment with depth along that pile segment. And what was encouraging is, so each one of these is the load level, and what was encouraging is that we found that the maximum moment was somewhere below the ground surface, which is expected for the free-headed pile condition that we were testing under. So the outcome here is that we felt good about is that we were able to get a good setup that seemed to giving reasonable data. As far as the pure loading test, this is again, this was Sean. Sean and his team fabricated the torsion alarm here. You can see it attached to the pile. Again, these with the actuators on each side, and then you can see here the string potentiometer attached there as well. The exact we're going to refine this down the line, but really the goal here was, again, just to get this set up and be able to apply some load and make some measurements. I don't have the data here to show you, but this was successful. We were successful at applying the load and measured displacements. So as far as next steps, so Juan Sebastian is actually living in Centralia at the moment and working hard on continuing the load test program with the Hubble team. In fact, also Hubble, he's actually staying in Hubble housing, which was a nice contribution to the project. But what they're going to be looking at moving forward for the remaining part of the summer is to look at things like investigating the size of the vane. As I mentioned, we have 3 different sizes that we fabricated. The monotonic behavior, both under pure lateral and pure torsional loading, as well as the interaction between lateral and torsional loading. If time permits, we would also like to investigate some other behaviors such as the creep response, as well as I mentioned the cyclic or fatigue response of the system. So fortunately, at the Hubble test site, there's plenty of space to do testing, and the site conditions are fairly uniform, so it's pretty ideal for doing repeat tests and things. And so Aaron put together these test areas, 20 foot by 20 foot. Each box represents an area that we could test, and you can see that we could perform up to about 80 tests here, which is nice to be able to have that opportunity. And just to summarize, so this is really was just to present some preliminary findings of our research and development project to develop this novel vane device to improve the lateral and torsional capacity of a helical pile. We hope if this works, it could be applied into lightweight transportation structures. We completed some initial field testing, and we were successful in the sense that we got our load test setups running, and the data seemed reasonable. The idea is Juan Sebastian is, as I said, is continuing his testing in the field this summer, and I think this is really a good example of how academia and industry can combine talent and knowledge to have a very effective and beneficial research project. So it's really an honor and a privilege to be able to work with the members of this team, and I look forward to continued work on this project over the next year or so. Thank you for your attention, and I'm happy to answer any questions that you may have.